Thank you. So we start with the introduction of the Hamiltonian, which has kinetic energy, electron-electron repulsion, and attraction with the nuclei. And you have to solve this Schrodinger wave equation. And if you could solve it and get the wave function from here, you can get actually all the observables of the system by calculating the expectation value of corresponding operator. So this seems quite simple, but it's quite challenging. For example, let us see. There are different ways to solve the Schrodinger wave equation. And if you want to calculate, say, this expectation value of any observable, you have to calculate this integral. It's an integral of many variables. Probably if you wait enough, it will go away. So we have to solve this integral over many variables to calculate any expectation value. And if we are doing so numerically, we'll have to select some grid over each variable. Say x1 represents the position and spin of the first particle, x2 represents the position and spin of second particle. So on each axis, you have to select some grid. You have to select some values on it. Then you will be able to calculate this integral numerical. Let us suppose we want to select a pretty naive or pretty poor kind of grid for those expectation value grids, such that on each axis, we just select 10 points. And on those 10 points, if you get the wave function, you can calculate the expectation value and get the observable. What would happen in that case? Let us suppose we have hydrogen atom, and with 10 grid points along each axis, I'm neglecting here the spin degrees of freedom, just using the spatial degrees of freedom. So along x-axis, you have 10 points. Along y-axis, you have 10 points. And along z-axis, you have 10 points. So on this grid, if you want to compute wave function at each point, actually, you need to calculate the wave function at 1,000 points. And if you, because 10 on each axis, so 10 values for x times 10 values for y, 10 values for z, so 1,000 grid points. So if we pick up a helium atom and do the same thing, then 1,000 points for one variable times 1,000 points for the second variable. So you will have to calculate this wave function on a grid of 1,000,000 points. If we go to oxygen atom, then we do 10 to the power 3 points for each variable, R1, R2, up to 8. You have 10 to the power 24 grid points on which you need to solve the wave function. And yes, more problem arises if you think of, if you calculate this kind of wave function on these many points, you have to store it. Assuming you go by the single precision with 4 bytes for each number, you have almost this many bytes to store. And it becomes 10 to the power 15 gigabytes. Probably the disk required with the, if you store it on a CD, the mass of those CDs would be as, and you keep on, you have endless supply of those CDs, and you weigh those CDs, the mass would be as big as this Earth's mass. If you go to the cobalt atom and you do again the same thing, you will need the wave function on 10 to the power 21, 81 grid points. And how big is this number? Compare it to the total number of atoms in the universe. 10 times the total number of atoms in the universe. And remember, I have neglected the spin degrees of freedom here. So solving the Schrodinger wave equation, even if you are able to solve, give you a wave function from which if you want to collect any information, you will have to do too many calculations, and you will have to store such a big data if you say want to solve the Schrodinger wave equation for the cobalt atom. And our systems, say solids and other systems, contain too many electrons, contain way, way, way many electrons as compared to, say, a cobalt atom. So hundreds of electrons could be in the system. So in that sense, just solving the Schrodinger wave equation to get the wave function, which has 3n variables, right? For each particle, you have x, y, z. With respect to space, you have 3 variables for each particle, and 3n variables if you ignore spin, and if spin is involved, 6n variables. So solving for this object of 6n variables is certainly not a practical approach. So you have to have some alternative approach to get your information with minimal resources and minimal storage capacity. So Dirac described this problem so elegantly that I would just like to quote him. The underlying physical laws necessary for mathematical theory of a large part of physics, actually he's talking about quantum mechanics, and the whole chemistry are thus completely known, and difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. So that brings us to the conclusion that if we want to use quantum mechanics for the practical problems with number of particles involved larger than, say, 27 or even 10, you probably need some approximate methods. And a number of approximate methods has been developed. Some of them really accurate, but computationally expensive, still expensive. And some of them, like DFT, are relatively cheap. I have listed here 2 methods, which I will use as benchmark methods. The quantity I will be mentioning here, for those quantities, my benchmarks would be coming from these 2 methods. One is the coupled cluster method, and the other is symmetry adapted perturbation theory. It's just the perturbation, regular perturbation theory, where you make the wave function anti-symmetric as required for fermions. And this coupled cluster method is just a fancy way of introducing the correlation of electrons amongst themselves. These methods are quite accurate, but they are still expensive. For n number of electrons, their cost goes to the 7th power of number of electrons. So if you double the number of particles, the cost would go up by 128 times. So if you solve for 2 electron system, whatever time it takes, for 4 electron system, it would be double. It would be 128 times larger as compared to 2 electron system, which is again too expensive, that if n is very large, we certainly would not like to use coupled cluster method or symmetry adapted perturbation method. If a number of this SAP with some special treatments, special approximations could be used for, say, hundreds. If number of electrons goes to, say, 100 or so, then this could be used. But coupled cluster method becomes difficult in those cases. So we need to develop an approximate method which is not that computationally expensive and which gives us a reasonable accuracy. Certainly, we will not be able to get as accurate results as symmetry adapted perturbation theory or coupled cluster method. Before I go to DFT, I would like to introduce the idea of dispersion interactions, which actually I did in the beginning. So if we have a neutral atom, for example, say this is an inert gas atom, then its electronic cloud gets polarized instantaneously due to quantum fluctuations. These quantum fluctuations will induce polarization in its neighbors, and the interaction of these fluctuations with their induced fluctuations gives rise to what is called van der Waals interaction. So instantaneous quantum fluctuations on atoms introduce instantaneous multipoles on those atoms. And those instantaneous multipoles interact with each other. Remember, it is different than the induced multipoles, which you get in the, say, if you put the atom in an electric field, it gets polarized. Or if you put an atom, you could get a molecule which is already polarized. For example, it's water. So these interactions do not involve permanent multipoles interactions. These multipoles are quantum fluctuations of the charges, and they are instantaneous. They are changing with time. So these interactions in physics are usually called van der Waals interactions, and they are pretty difficult to deal with in density functional theory. In symmetry adapted perturbation theory, this dispersion interaction energy has very rigorous kind of definitions. You can define the dispersion energy up to second order in the interaction between two monomers in terms of the interaction potential and the wave function for each of the monomer. This 0 denotes the ground state wave function, and these K and L, which are not equal to 0, represent the excited states of those monomers. These excited states are actually are describing those quantum fluctuations of the charges. And one could write this expression of the dispersion energy in terms of the density response function. It's just a fancy name to describe how a perturbation in a charge density would affect that charge distribution of charge density. So it's the same thing as this, just we could rewrite this expression in these terms. The difficulty in this kind of expression is that it involves integration on 3 here and 3 here and 3 here and 3 here, 12 spatial dimensions and 1 frequency. 13-dimensional integration is involved in here. So for those people, say Rafi has worked in coding different DFT methods, and those people who work on numerical integration, they understand how difficult it becomes to integrate if dimensions go very high. So this is too complicated a problem to solve. Actually, we could solve it, but that would be very computationally expensive. So we want to solve this equation in an approximate way and get the dispersion energy. So my benchmark dispersion energy, in whatever way the dispersion energy would be calculated later on in this talk, that would be compared with the dispersion energy calculated from this expression of symmetry adapted perturbation theory. Actually, one component of it comes from the anti-symmetrization part. If you use anti-symmetric wave functions, you get dispersion energy and then the exchange dispersion energy. That's actually the effect of using anti-symmetric wave function in the dispersion expression. So the benchmark quantity here, Edisp(x), involves dispersion energy and exchange dispersion energy. That represents actually the total quantum mechanical magnitude of the dispersion interactions in quantum mechanics. Yes. Yep. Could be anything, any atom, any molecule. You could use it for anything. You have to solve for it. Yes, you have to calculate those wave functions. Oh. आपको क्या करना है? Okay, so in perturbation theory, we start with the Hartree-Fock orbitals and then build down corrections. Yeah. Our guess usually the starting wave functions are Hartree-Fock wave functions. Well, if you know the linear response theory or response theory, you can get these quantities in terms of the wave functions and energy differences and replace these expectation values with this kind of quantity. It's just how it measures how the perturbation would affect the density. So before going to the density functional theory, I would like to define the electron or density of any number of particles. If you know their wave function, you take the modulus square and integrate over all variables except one. You get the probability of finding a particle at that point. Actually, if you multiply it with the volume element, you get the density in the real sense. You get the number of particles, the probability of finding the particles in that volume, right? So in that sense, this is electron density, number of electrons per unit volume, you can call it in a simple way. So probably you know already this part that if you integrate wave function over all variables, you get the probability, right? The probability is integration over all variables of the modular square of the wave function. And if you don't integrate over one variables, it becomes probability density with respect to that variable. So it gives you the number of particles per unit volume. How does the density functional theory works? What are its bases? So now density functional theory claims that the basic quantity which we need to know to calculate all the variables is the electron density. And if you know the electron density, you will should be able to calculate all the variables related to the system. So like in wave function theory, wave function, which is a function of 6n variables, is the basic quantity which contains all the information. In density functional theory, we have a function of 3 variables, so quite easy to handle, say in numerical sense, and storage as well. This variable contains all the information about the system. So there are 2 theorems which prove this claim. The first one is Hohenberg-Kohn theorem, which says that ground state density uniquely determines the external potential and the Hamiltonian. External potential is interaction of electrons with any external source, could be nuclei or any other potential if you have some other source of field. You have applied some external field then, even then. So nuclear field or external field are in here. So density uniquely determines the external potential and hence the Hamiltonian. So it means they have one-to-one correspondence. Knowing the density means knowing the Hamiltonian, and knowing the Hamiltonian means actually we know the wave function in principle. So there is a unique correspondence between density and the Hamiltonian. And if you know the wave function, if density uniquely determines the external potential and Hamiltonian and the wave function, actually it uniquely determines all the observables, because all observables would be the expectation value of the wave function. So if Hamiltonian is a functional of density means it determines uniquely the Hamiltonian. It means density determines all the observables uniquely. So that's why mathematically we could call that all observables and Hamiltonian are functionals of density. They could be uniquely determined if we know the density. That's the claim, right? Well, there exists part, its time-dependent part exists, which is similar. So you could take it pretty general. Time-dependent case exists. Time-dependent DFT also exists, and this theorem holds for time-dependent cases as well. And the second, yeah. And the second theorem says the energy is a functional of density, because like all observables, energy is one of the observables and the most important observables. Energy is minimum if you use the actual ground state density. This relation, the second Hohenberg-Kohn theorem, gives you the recipe how could you work with DFT. If you calculate the energy using some density and then minimize the energy with respect to density, of course, a legitimate density, the minimum of energy would correspond to the ground state energy, and corresponding density would be the ground state density. So the second theorem is actually tells you that you could determine the ground state energy and ground state density using the variational principle, like minimize the energy with respect to density. In simple words, just take the functional derivative of the energy with respect to density and put it to zero, equal to zero. So you will get the ground state energy and ground state density. So if these two theorems have quite simple proofs, any textbook could be consulted for those. But there is a problem. To minimize the energy, we need to know the functional form of energy with respect to density. We need to know how kinetic energy is a function of density. The two theorems just propose or just prove that such a functional exists, but they do not provide any form for the kinetic energy and any form for electron-electron repulsion energy. So we do not know these forms. This form actually is easier to tackle with, this external energy. Just integrate this function by multiplying it with the density, and you get the external energy. So this form of energy from this term is easy, but these two terms are difficult to deal with. We do not know their functional dependence on the density. Yes. Yes. So external potential is potential provided by the nuclei or any other external source. Anything other than electrons. So we do not know its functional form. So although these theorems show that we could uniquely describe functional in terms of density, or any operator or any observable is a functional of density, and we could get that density, ground state density, by minimizing the energy with respect to density. But it does not give any prescription. How will we deal with these two terms? And these two terms are present in every system. So they are universal terms. Sometimes some books will call these the universal functional, denoted with F of n. This square bracket is for denoting the functional. Functional is something which maps functions on numbers, like functions map numbers on numbers. Functionals map functions on numbers, like definite integrals. You give a function and integrate over definite limits, you get a number. So exact DFT is unknown because we do not know the form of the kinetic energy and electron-electron repulsion energy as a functional of density. Kohn and Sham went around this problem. How did they go about it? They say the main problem here is this electron-electron repulsion energy, which couples one electron with the other electron. If this term is not present there, the corresponding Schrodinger wave equation will have kinetic energy and interaction with the nucleon. The particle will just behave as if they are independent particles. And for independent particles, the n particle wave equation or Schrodinger wave equation can be split into n single particle wave equations. So you can split single equation of n particles into n equations, each for single particle, if this term is absent. So what did they do? They assumed that we have a fictitious system of non-interacting particles. And for this non-interacting particle system, we can solve the many-body equation quite simply, because this equation just splits into single particle equations. But if we use this, which was called external potential here, this part, interaction, this is the external potential, and this is the electron interaction of particles amongst themselves. So Kohn-Sham system turns off this part and adjusts this part so that the corresponding orbitals give the same density as the actual system. So if we appropriately adjust this external potential by turning off this electron-electron repulsion, and we adjust this term, we will see shortly how much we have to adjust it. Then we will get the density. And this density would be the same density as the actual system of interacting particles if you appropriately adjust this term and get this VSR, which is called Kohn-Sham potential. So Kohn-Sham DFT solves for a system of non-interacting particles in a kind of effective potential and such that those particles are not interacting with each other, so that each time we don't have to solve many body wave equation, which will be like n coupled Schrodinger wave equations. Now we will have n equations for each particle, and those equations will not be coupled. So by doing so, we can get the kinetic energy as well by using the orbitals. So Kohn-Sham approach gets the density by solving a single particle equation and gets the kinetic energy by using those orbitals from which it got the density. In that sense, Kohn-Sham DFT should be called density depending on the density function and depending on these Kohn-Sham orbitals as well. So in that sense, it's not a truly density functional theory. It's a theory which depends on density function and orbital. So how is it useful? We'll see shortly how getting the density of the actual system from a system of non-interacting particles, how would it help us? Let us see. The actual Hamiltonian for which we have to solve the problem contains kinetic energy, electron-electron repulsion, external potential, attraction with the nuclei, or whatever external potential. Corresponding energies are kinetic energy, electron-electron repulsion energy for this, and this is external energy. We split this total kinetic energy into two parts. So we say that kinetic energy of interacting particles is equal to kinetic energy of non-interacting particles plus some correction. And we don't know what is this correction as for now, right? We can write this Tn is equal to Tsn. Tsn is the kinetic energy of non-interacting particles. Wherever you see this subscript S is actually a Kohn-Sham quantity. That quantity corresponds to the system of non-interacting particles. So we split this kinetic energy into kinetic energy of non-interacting particles plus a correction, which is due to the correlation. Actually, particles are correlated. And then electron-electron repulsion energy, we split it into two parts. One is the classical Coulomb repulsion energy, which is this. So repulsion between electrons is calculated by using the electron densities. So you could call it the electron density if you have an electron density n of r, and you want to calculate interaction of it with itself, you calculate this integral, right? From electromagnetic theory, if you know this integral. I think it's pretty much commonly used integral. Electron density at r, electron density at r prime, over r minus r prime, and integrate it. And this 1/2 avoids just double counting. This integral double counts the Coulomb repulsion between different points. So this is actually the Coulomb repulsion law written in terms of the density. First charge of the first particle times charge of the second particle over separation between the particles. So it's the same thing. It is called Hartree energy. Just a technical name. It has some historical background, but it's a Coulomb repulsion energy. It's the same Coulomb repulsion which you will have for classical kind of distributions. So this Hartree energy has all classical repulsion effects included in itself. And whatever is left over, this delta EE, whatever correction we need to make this sum equal to this electron-electron repulsion is in here. This is correction to it. If you add this delta EE to this Hartree energy, you get the actual electron-electron repulsion energy. So doing so, we collect these corrections to the kinetic energy and correction to the electron-electron repulsion in one term, which is called exchange correlation energy. So the exchange correlation energy in DFT contains kinetic energy of difference of kinetic energy of a system of interacting particles with the kinetic energy of non-interacting particles. So this delta T is equal to Tn minus Ts. And this delta E is electron-electron repulsion actual minus this Hartree energy, right? So this exchange correlation energy includes correction delta T plus delta E. From here, you can write that exchange correlation energy has a difference of kinetic energy of non-interacting particles and interacting particles for the case when the two densities are same. And in the similar way, electron-electron repulsion and Hartree energy, which is Coulomb repulsion of electron density with itself. So exchange correlation energy has two contributions, kinetic energy contribution and electron-electron repulsion contribution. So all many-body effects, how the particles are correlated, all many-body effects are included in this exchange correlation energy, because this rest of the quantities are very simple. This kinetic energy of non-interacting particles. This Hartree energy is Coulomb repulsion for classical densities. This external interaction energy doesn't matter, you take it classical or quantum mechanics, it will be the same. This exchange correlation energy includes correction to this electron, this Hartree energy and this kinetic energy, which you need to make if you have actual system of interacting particles. So you should expect that this exchange correlation energy includes all many-body effects in it. So yes. Well, it's in principle, it should be included here. So if you are talking about the Hartree folk kind of exchange, DFT exchange is somewhat different than that. I'm not sure. What do you mean? I mean, if like you have like say you triplet energy difference which arises from the spin synchronization. Yeah, well, that would be involved. So this exchange correlation energy has two contributions from kinetic energy and electron-electron repulsion. All functionals which you see in DFT are an effort to approximate this exchange correlation energy. Exchange correlation energy is probably about 1% of the total energy. Very small as compared to all other terms in this total energy. But this is the most decisive part of the energy, so much so that if you ignore it, you won't have bound states. So it's too important. Very small term, but all efforts of the DFT, those people, not those people who are trying to apply DFT, those people who are trying to develop DFT methods, they're trying to approximate this exchange correlation energy. And this exchange correlation energy is the term which includes that dispersion interaction, because it includes the many-body effects, all the many-body effects, how the electrons in the actual system are correlated with each other. So it includes all that stuff. So we should be looking towards exchange correlation energy if we want to see dispersion interactions in here. So DFT divides the total energy into four parts: kinetic energy of non-interacting particles plus Coulomb repulsion of the density and attraction with the
I can understand that the exchange correlation is going to have the positive effect, but downstates just come from the energy with the external field.
It's hard to explain for now. So if if you think I would prove here there would be some proof. I don't have any proof.
I just give you a very simple scenario where I just have it, the hydrogen atom. I don't have any correlation at all. I do have an external field, and that external field is still giving me my balance. I would imagine.
I have an example where I will let you know. So think of two inert gas atoms.
Okay.
So how would you bond them?
Oh, absolutely. Yeah. That I can understand. That I can.
So we have two argon atoms, for example. So how would you bond them?
No, I mean, I just say that they're just free.
Then it doesn't matter to you if they are bound or not.
Exactly. We're talking about slightly different things. That's all. Sorry.
Okay, maybe we can discuss if you think about that. So it divides it into four different terms: Kohn-Sham kinetic energy, Hartree energy, and external energy, attraction with the nucleus, and the exchange correlation energy. I wrote down here this kinetic energy, Hartree energy explicitly here, and external energy using density, and exchange correlation energy. So all functionals are effort to approximate this exchange correlation energy. Those functions which approximate exchange correlation energy just using the density are called local density approximations. Those approximations which involve density and its gradient are called generalized gradient approximation. And then you have kinetic energy density dependence. Those are called meta GGAs. So there are a lot of terms and a lot of names. Each effort is just an attempt to get this exchange correlation energy precisely. And it's quite difficult. It's been intractable as for now. This exchange, there is an interesting way to visualize this exchange correlation energy. If an electron is present at a point in space, it produces a deficiency of electron density around it. Obviously, one reason is Coulomb repulsion. The second reason is Pauli's principle. So that deficiency of density around that electron could be called a hole. So attraction of electron with that hole could be called the exchange correlation energy. So exchange correlation energy could be written in terms of Coulomb attraction between N of R, which is the density of the system, times the exchange correlation energy density. So this is the hole, exchange correlation hole. This is the deficiency in electron density around the electron due to Coulomb repulsion, due to Pauli's principle. So you can visualize exchange correlation energy in these terms. The problem with all the DFT methods is that they assume that this exchange correlation hole has range of the order of an angstrom. There are some technical issues here. If they use some other way, they get nonsensical results. So most of the methods assume that this exchange correlation hole is of the range 1 angstrom. which would mean this exchange correlation energy would be calculated between electrons which are separated on average by a distance of an angstrom or less. For those electrons which are outside this exchange correlation hole, there will be no exchange correlation energy. In that sense, we could say that DFT approximations are myopic. Electrons cannot see beyond an angstrom or so. So we expect that this exchange correlation energy, due to short-sightedness or short range of exchange correlation hole, will be missing long correlation effects, which are called dispersion interactions. Don't worry. The stage is all set, so it will wrap up. Don't worry. So this short-sightedness of the exchange correlation hole makes those part of exchange correlation energy zero for those electrons which are separated by distance more than an angstrom. So it misses the long-range correlation effects, long-range exchange correlation effects, actually. This is a graph showing that DFT is quite popular. I don't think I need to tell this to anybody. So here is a system, sir. We have a system of two argon atoms for which the interaction energy is provided by the interaction of instantaneous multipoles. This is about 3.76 angstrom. This red and blue lines are benchmarks, CCS, DFT, SAP, very accurate wave function theory methods, produce almost exact interaction energy, and almost entire interaction energy in this region is due to dispersion interactions. So if those interactions are not here, no two argon atoms could have a minima. In that sense, I was telling it. So I have tested a number of methods, include LDA method, GGA, meta GGA, even hybrid methods are tested here. Due to short-sightedness of holes, there is a class of DFT methods called DFT+D methods, which corrects DFT for the dispersion energy. These methods assume that dispersion energy, that long-range correlation effects, is the only problem of the DFT. And the part of the long-range correlations which DFT is missing, if you correct DFT for that part, then you should get the exact results. So here the correct DFT for dispersion energy, the deficiency, assuming that only deficiency in DFT is due to missing long-range correlation effects. So in this figure, we prove that missing dispersion interactions is not the only problem of the DFT. DFT has problems in other terms as well. For example, this is an interaction energy of argon and lithium plus. And here we have dispersion energy, and we have plotted ratio of interaction energy to the benchmark interaction energy. We see very small amount of dispersion energy is present here in argon and lithium plus, but still the error in the interaction energy for this case is up to 20% or so. So This 20% error cannot be produced due to missing parts of a quantity which is just 5%. So DFT has other problems than just missing dispersion energy. So how do we compute the dispersion interactions recovered by the DFT? You have already seen that there is no explicit term for dispersion interactions. We have a benchmark interaction energy from coupled cluster theory, benchmark dispersion energy from symmetry adapted perturbation theory, and we take the difference to get the dispersionless energy. So if you assume that DFT has dispersionless energy correct, but dispersion energy is not correct, then difference of DFT energy with the dispersionless energy should give you dispersion recovered by DFT method. So I have tried to explain it here. You split the DFT energy into a dispersion part and dispersionless part. And if you subtract the benchmark dispersionless energy from it, if dispersionless part of DFT is same as dispersionless part from the rigorous theories, accurate theories, then this difference should go to 0. And it should represent, E extra should represent the dispersion recovered by DFT methods. And if this E extra is the dispersion recovered by DFT methods, you can correct it such that this E extra becomes equal to this benchmark dispersion energy. This is the approach all the DFT+D methods apply. They assume that there is no error in the dispersionless part of the DFT energy. But as for argon and lithium plus, we showed that there is definitely a problem in DFT other than dispersion. So what should be the expected behavior of this E extra, which is apparently the recovered dispersion energy by a DFT method? It should be like, there should not be any dispersion energy recovered by a DFT method at large separations. When two argon atoms come closer and the charge cloud starts overlapping, they come sufficiently close so that the particles, the exchange correlation holes will have overlap, and then exchange correlation energy will have non-zero value, and then there will be some recovered dispersion energy. That's why we expect that this ratio of E extra to E dispex would be like this. When atoms overlap too close, then 100% of dispersion energy should be recovered by DFT. So this should be the behavior of E extra ideally. So we pick up the best three methods: scan, TPS, SPB, LDA. One of the best methods, amongst the best methods, is this scan functional, which satisfies all known physical constraints. And we see that behavior of this E extra is qualitatively similar, but quantitatively different. At large distance, we don't have any recovered dispersion energy. At small separations, 0 or very small, 1.5 angstrom, it does not just go to 1, it goes up there. So what appears to be the recovered dispersion energy is actually here about 40% more, here about 25% more, here is about 20% more. So the behavior of this E extra shows that it does not have only the dispersion contributions. It has contributions from other errors which needs to be corrected. So where should that dispersion energy come from? This dispersion energy should mainly come from the correlation term and the exchange term. So here we show this E extra our E specs, E extra over E specs for the scan functional, which becomes a little bit more here when close. The other thing is close to the minima, it is almost recovering about 90% or 80% of the dispersion energy, which is not expected. At 5 angstrom separation, where there will not be any overlap of the clouds, it is recovering about the 50% of the dispersion energy. And this correlation contribution is about 50% of it. The rest of the, for example, it's half of the dispersion energy is being recovered in E extra. And only half of it could be accounted for by the exchange term, by the correlation term, this one, this yellow one. So it is, this value is about 0.5 and this value is 0.25. It should get some other contribution from some other term. It cannot get any other contribution from exchange part because exchange part has opposite sign. Exchange contribution is below 0. So this E extra can certainly get contribution which has the same sign as dispersion energy. These are negative contributions from the correlation part. But the difference of this correlation and E extra, which we expected that it should come from the exchange part, that cannot be from exchange part because exchange part has opposite sign here. Okay, that's why we should say that this E extra has contributions from those terms which are not in exchange correlation energy. And if this E extra has contributions from those terms which are not in exchange correlation energy, those effects are non-physical. Those terms are not designed to take into account the many-body effects. That's why the current state of the art DFT functionals need more constraints to restrict the behavior of each term within their physical limits. That's all from my. So what appears to be the dispersion energy from DFT is actually includes recovered dispersion energy by DFT methods plus errors of the other terms. And DFT+D methods are adding a correction to correct the missing dispersion energy plus errors of the other terms, which is you are getting the right results for wrong reasons. That's all.